Hi there and welcome to the screencast for Workshop 3. So you can see when I loaded the Lab 3 Markdown file up, I'm getting this nice little message along the top that the Simputation package is required but not installed, and I can be prompted to install it. If you're on a Windows or a Mac, I think this is in a yellow bar, but it's still quite subtle, so be on the lookout for it. Of course, I could just install that package later. Let's install it now. So it's working away there. Might take a little bit because I think we have to do some code building here by the looks. If you're on a Windows or Mac, it will probably just read in directly the binary version. You can get binary versions for Linux as well. I just don't have it configured here. If you Google R universe, you'll come across those. But we'll just wait for a bit. I'll pause the video until it's done. Okay, so that's done. So now I can run that first code hunk, which reads in the husbands and yeast data. I should have these up here. Yes, there we go. Excellent. Just a note that we'd use include equals false here in this R header. This is where you put options for your R code chunk, and so this stops the output from a lot of these libraries. So like when you load the tidyverse, it spits out a bunch of messages. So it just suppresses those messages, including the output from the read CSV. Okay, so we're going to be looking at missing data today, and we're going to start by looking at the husband's data set. And you'll see here that I've got an odd value in the wife's age column. Okay, so this data has been encoded with a special number for the missing value. And so that's useful to be aware of, that this can happen, and that any summaries, numeric summaries that I do of the wife's age are going to be wrong if they use the values. Okay. So one thing we can use to look at a data set in general is we can type it out like we've done here, or we can use the skim package from the skim R, the skim function from the skim R package, which produces one row per variable. So here we've got the husband's age, the husband's height, the wife's age, the wife's height, husband's age at marriage, and then summarizes the data. So you can see we've got the number missing, which is 0. Because there are no missing values in this data set so far, because they've been encoded as numbers. So obviously RStudio doesn't know at this point that they're missing. The completion rate is 1, which is 100%, and then you can see that the mean is sensible for the husband's age and probably the husband's height and the wife's height, but it's very much not sensible for the wife's age and the husband's age at marriage. And there's various other things. So you get a wee histogram here, and you can see that these two here have very skewed distributions due to that large maximum value. As you can see, all the other values are sensible, but there's a weird maximum value. These are the percentiles. So to fix this, we can use the replace with NA function in the Narnia package. So replace with NA takes a list for the replace argument, and the items in that list are the column names that you wish to process and the values that you wish to replace with NA. So in this case, we're replacing the 9999 special coded values with NA. And when we do this and then skim on the resulting husbands underscore NA set, you can see now that we have the missingness. So we've detected the missing, so we've corrected the data set to include the missingness, so the completion rates are here, and now you can see that the distributions look sensible in that histogram, and the values look sensible, the means look sensible. Okay, so it's just something to look out for. So we've got another data set here, the yeast data set. And we're going to see the same thing. So if we have yeast and we throw that at skim, then we see we have a whole bunch of variables and none of them are missing. Okay, so if you go down, all of these variables, which are all genes, I think, I'm not really sure. And you can see that a lot of these variables have this 999 number, yet every other number is much more sensible. Okay, so 999 is being used to encode missingness here. Okay, so we could replace the missingness. So we could do the same thing we did before. So we could just use replace within A and then supply a list where we've just fill in the column names. So if we go back over here to have a look at them, so we had alpha 0 and alpha 7, sorry. So we could say alpha 0 is 999 and alpha 7 is 999, and we could continue on, right? And then when we have a look at that one, we can see that those first two columns we've identified the 57 and 62 missing values. So we can see now that the mean is something closer to 0, which is perhaps what we might expect, given that these data have been normalized in some way by the looks. Okay. Now, obviously, we would need to do that for all the others as well, and so that's what the replace within a all function is. So let's make another one where we use that. Okay, and so we just need the condition here. So let's have a look at that. Help for that. So a condition required to be true to set NA. Here the condition is specified with a formula following the syntax like this. Right, so for example, writing tilde.x less than 20 would mean where a variable value is less than 20 replaced with NA. So I think the idea here is that we'd go .x equals 999. And then we're going to skim that. And there we go, we've correctly identified all the missingness, and so now you can see that the means are all somewhat sensible, and the histograms now look a little bit more sensible as well. Okay, so that was just throw a skim in there. Right. Okay. So that's how to check for things like numbers that are missing. But once we do have our missing values in the data set, it's useful now to assess where those missing values are. And so we can visualize the pattern of missingness in several ways. So one of them is with the vismiss function from the Narnia package. And so you can see that this does a classic matrix view or a heat mappy type thing, where we've got our rows or observations on the y-axis here, and we've got our columns or variables on the x-axis. And you can see that it's black if it's missing and grey if it's not. So you can see that there's perhaps 4 missing values here in the husband's age at marriage, and there's a whole heap missing in the wife's age. Okay, so it's just so that you can kind of get a sense for where the missingness is. So for example, you're looking to see whether you have rows that might have a whole bunch of missingness in them, whereby you might want to remove that observation, or you're looking for columns that are predominantly missing, which you may like to remove as well. So one thing we're potentially interested in is, could we use, so we don't know the husband's age at marriage for 4 records by the looks, but potentially we might be able to use the other information, including the wife's age, to try and impute what the husband's age at marriage might be. But that's only going to work if we actually have the wife's age. Otherwise, we'll just have to use the other columns, which is fine. But the question is, are these missingness? Are these ones that where the husband's age at marriage is missing? Is it more likely that the wife's age is missing there as well? So one way to do that is we could filter based on whether the husband's age at marriage is missing. So is it not available? And then if it isn't available, we then throw it at the visualization. So here you can see that we only return the 4 rows where the husband's age at marriage is missing. And you can see that there's actually only one observation where we have the wife's age. So there is some more likely to be missing the wife's age if the husband's age at marriage is missing. So another set of useful plots are GG Miss var, which is looking at creating a plot of the variables and how many are missing. So you can see that wife's age dominates, right? So there's 29 missing values, and husband's age at marriage has 4 missing values, and the others have none. And then the other way round is GG Miss case, which is telling you about the cases. Okay, so you can see that there's a small number, I think it's 3, that have 2 missing values in them, and then there's another set that have just 1 missing. So these are the ones that have both wife's age and husband's age missing, and then this set here are the ones that have one or the other missing, mostly the wife's age. Another one is the upset plot, which is this, produces this result here, and it shows you all the combinations of missingness. Right, so the husband's age at marriage could be missing, or the wife's age could be missing, or both could be missing. So here you can see the pattern here is that just the wife's age is missing because the black dot is next to the wife's age, and there's in total there's 29 in the wife missing and 4 in the husband's missing. So the ones where just the wife is missing, there are 26. The ones where just the husband's age at marriage is missing, there's only 1, and there's 3 that both are missing. So in this upset plot, the line here represents that both are missing at once. And if you had more variables missing down here, then you would have other combinations, obviously. So next we want to know, okay, so the wife's age is the one that's sort of the most missing. Next we want to know whether the missingness might be associated with the age or with some other variables that we might have in the data. So we're not going to be able to infer necessarily that the missingness is associated with the wife's age because we don't have it, obviously. We might get a sense of that by checking whether the wife's age is associated with some of the other data that we have. So you remember there's 3 types of missingness. There's missing completely at random, where whether something is missing or not does not depend on the data that we don't have, i.e. the data that's missing, and also doesn't depend on the data that we do have. So it's just pure randomness. The second option is missing at random, where the missingness is not dependent on the thing that is missing. So in this case, the missing values of the wife's, whether the wife's age is missing is not dependent on the wife's age, but might be dependent on some of the other data that we do have, such as the husband's age. Okay, so we want to assess that, and then missing not at random is where the missingness is dependent on the thing that is missing. Okay, so that's kind of the worst case, right? So the wife's ages that are missing in our data might be all older or younger or something like that. Okay, so one way to sort of check for this is to just do a plot of the data that we do have to see if there's any relationships present that we might be able to exploit in order to sort of fill in the missing values in the wife's age. And we see that there's a very clear relationship. It kind of makes sense that people do tend to partner with other people that are of similar age to them. So we get this sort of increasing trend. It's not super strong. There is obviously some outliers where you have an older husband here with a younger wife, or an older wife with a younger husband, and so on. But it's relatively it's a relatively straight relationship. So now we want to be able to assess what about the ones that are missing. Well, the ones that are missing, we don't know what the wife's age is, but we do know the husband's age. So we can at least see where they appear on this plot with respect to the husband's age. And we can do that with a geom miss point. So again, this is in the Narnia package. And so you can see here, this plot's the same data that we had before. So this is the data that's not missing. But then it adds an additional row down here where the y variable does not matter. It's always put below or above, depending on your settings, the actual wife's age, so that we don't know the wife's age for any of these, so we just sort of put them down off the end of the data, but we do know the husband's age. So the thing that we notice is that it's reasonably uniformly scattered along here, right? So it doesn't, whether the wife's age is missing doesn't seem to depend on the husband's age, at least, because across the board, across the range of husband ages, there's missingness. If they were all gathered at one end or the other, or sort of more at one end than the other, then we might have an inkling that that the missingness is dependent on the husband's age. Right, what about the husband's age at marriage? Let's have a look at that. So take a look at the relationship between husband's age at marriage and wife's age. So again, we could do exactly what we did before. So we're going to plot the husband's NA data. So we could just do a G on point. So husband age at marriage, and Y is going to be the wife's age. So this would be the complete data, and we can see that there's not a strong trend here. And then we could look perhaps at the incomplete data. And again, we notice that that doesn't really seem to be a strong pattern here. So the missingness in the wife's age is down here, and you can see that that's sort of scattered across the range of the husband's age at marriage. The one up here is the one where the wife's age is present. So we have the wife's age is 53 by the looks, but the husband's age at marriage is unknown. Okay, and down here is where they're both missing. So we don't have any idea about this set down there. Okay, so we'd say that husband's age at marriage is not strongly useful for inferring what the wife's age is. Okay, and then visualize the missingness in the yeast NA data. Okay, so we're going to look at just a couple of columns. So we could do some of the ones that we did before. So let's have a look at those. So we've got these ones here, perhaps. So I can have a look at this one. It's going to take a bit longer because the yeast data is quite large. There we go. So yeah, there's quite a bit of missingness in a lot of the variables here. There don't seem to be any clear sort of vertical stripes or horizontal stripes. I mean, some are missing a bit more than others, but it's all sort of much of a muchness. No horizontal stripes, which really, I mean, I guess there's maybe some smaller ones here, so some of the rows might be slightly more missing. What else could we try? We could have a look at the missing vase. Okay, so you can see that alpha 28 is the most missing, and it varies a bit. There's a couple that aren't missing at all, which are identifiers, I think. So a few of them are slightly more missing than others. What about our variables? Our cases. Yeah, so we've got a case that's missing about 8, or a few cases that are missing up to 8 of the columns, but most of them aren't missing too many. So it doesn't seem to be highly clustered within one or two observations. So we're not going to just be able to sort of get rid of a few rows and save this. So we might want to look at the first two alpha columns. So we might want to do one of those miss points. So we could look at alpha 0 and alpha 7 perhaps. So you can see that there's some, maybe some trend. It's not really clear. We can see that where the missingness is in the alpha 7 and in the alphas, in the alpha 7, which is down here, and in the alpha 0, which is over here, is mostly where the middle of the data are. So that doesn't seem all that surprising. So we could perhaps write something here. Okay. So then, now that we've visualized our missingness, how could we perhaps infer what those numbers are? So one way to do this is to use the impute mean function. So what this does is basically takes the column that you pass to it and replaces any missing values, or so computes the mean of the non-missing values. So those are the values for which we've observed the wife's age, and uses that for the NA values. And here we're overriding the existing column, so essentially we've fixed the wife's age. Okay, we won't have changed the mean, of course, because we've replaced the new observations, so the values that we're missing, with the mean, so the mean will stay the same. The standard deviation would have got a little bit smaller because we've put observations exactly at the mean, and you remember the standard deviation is the square root of the squared distance from the mean. So we've added a bunch of observations at the mean, and so they have distance 0 from the mean, and so they're going to be pulling the standard deviation down a bit. So instead of doing this, we could use here we've overridden the old column with the imputed one. Instead, we could use a different column. Right, so we could just do the same thing. Right, we just create a new column. Impute mean. And then we could have a look at that one. Right, so you can see here that the mean for my imputed one is the same, but the standard deviation is reduced, just like I was saying before. Now that we have the two columns, we could actually use that information to plot it. So we could for example look at the husband's age versus the wife's age, which we knew was. We could look at the imputed age, and we could colour it based on whether the wife's age is NA. Right, so you can see here's our imputation here. So if the wife's age was NA, we get the sort of the bluish colour. So those are the observations that we've imputed, and those are the observations that we aren't. So you can see the imputation here has broken the relationship between husband's age and wife's age. Another couple of ways to do that would be using bind shadow. So bind shadow basically adds new columns for whether or not the thing is NA. So it fills it with not NA or NA. And so we can override the existing column, and then we can color by the W age NA extra column that we added with the bind shadow. Okay, so that's a quite handy function for visualizing. So another thing we can do is k-nearest neighbors, and k-nearest neighbors essentially uses the information from the relationship we have. So instead of just using all of the wife's ages to impute the wife's age at this value here, instead we take advantage of the relationships present in the data by finding observations that are similar to the one that's missing. So for example, has a similar husband's age, and then looks at what the wife's ages are on those people, those couples. So for example, where if you look at the husband's age that is close to 24, down here you'd find that the wife's age is much more likely to be something like between 20 and 30, for example. Whereas if you were trying to impute this one here, which is 63ish, 62 I think, then the husband's age is 62, then you might use these observations up here where the husband's age was close to 62. So you might infer that the wife's age is up around the 60s as well. So when we run KNN from the Vim package, we specify the number of nearest neighbors that we want. And what that does by default is it adds these additional columns for whether or not it is imputed that variable. So by default, KNN will impute anything that needs imputing among the columns that you pass to it. So here we've passed the entire data set to it, so it's going to be using all the data sets, all the columns. Obviously, it just has to impute the wife's age and the husband's age at marriage, and it's going to use all of the available information to do so. And then it'll add these additional columns, one for each one, telling us whether it imputed. So you can see here we've imputed the wife's age for observation 8. So now we could plot that, right? So it's done the imputation, so we know that the original ones, that wife's age column now has the imputed entries in it, but we can now color by this variable the imputed the column that tells us whether it imputed or not, and that then allows us to visualize where the new observations are. And so you can see here that it does a much better job than mean imputation. So we're going to try altering the k. So how many nearest neighbors should we choose here? So let's just take that same code and we will we'll try different values for k. So let's try k equals 1, say. So this will just be using one neighbor. Okay, and you can see that it's a little bit more variable. You can see that something odd's happening up here with these observations here. And this is possibly because the observation that we've chosen would have had a similar husband's age, but may have also had a similar thing on some of the other variables. So we're not using just husband's age here, we're using the other variables as well, and they may be influencing those points. What if we increase k, so say k equals 10, then again that does reasonably well. If we go too high, then it starts flattening out. And the reason that it starts flattening out is we're now using 100 neighbors. There's only 200 points in the data set, so we're using about half the data to impute the ones down here and about half up here. And as we crank that up even higher, will it let me do 200? Yeah. It just drops back down to mean imputation, right? Because I've specified that I've got to use 200 neighbors, and 200 neighbors is the entire data set. So all it's doing is finding the average of the 200 nearest neighbors, which is the entire data set, which is mean imputation. Okay. Right, so let's just maybe write a quick note on that. So with k equals 1, sum of the points off the trend, possibly influenced by the other measures, the other variables in the data. Husband's age at marriage, husband's height, wife height, etc. With k equals, with k very large, we're averaging over many neighbours who are maybe not very close. With k equals 200, this is the entire data set, so we're back to mean imputation. Okay. What about the yeast NA dataset? So we're asked to just play with the alpha ones. So let's select out columns that start with alpha, just so that we don't have too many. K nearest neighbours is fairly computationally intensive if we've got many columns. So now we've only got 18. And then we could perhaps look at the relationship between alpha 0 and alpha 7, so the first two, for example. I didn't do ggplot, did I? There we go. And so now we're going to do imputation on this. So let's maybe run k nearest neighbours with k equals 5. And then we could colour by the alpha 0 imputation column. So you can see this takes a little while, but you can see where the values have been placed. So there they are. Now I've done it around the wrong way, really, haven't I? Because I'm plotting the ones where alpha 0 has been imputed, but normally that would sort of make more sense on the y. So let's swap that over. We'll rerun that, and then we'll maybe have a look at k equals 1 and k equals 1000 as well. See what happens. Right, so you can see that there's some scatter of the points, but there's not really a big trend here, mostly because there's really not a very strong trend in this data anyway. Let's try k equals 1 and see what happens. Oh, sorry, this is geom miss point. I probably don't need that, do I? I can probably just do geom point, because nothing's missing anymore, is it? So here's k equals 1. Perhaps we'll do k equals 1000 as well. Now it's put the points underneath. So if we want them on top, we could first arrange by alpha 0. So that it renders the blue ones last. So that we can see them. Could add some alpha as well, maybe. Alpha to the alphas. Just so that we can see through those observations a bit. I don't know if that'll help. Got a lot of observations here, 2000, over 2000, so. Let's do the same with k equals 1000, see what happens. Just grab all of that. So obviously we're using a lot of neighbours now, some of which aren't going to be very close to the actual observations anymore. So we might expect that that the imputation is very close to the mean, which is what it is. Okay, so one of the key things with k nearest neighbours is sort of choosing how many to do. 5 is a good rule of thumb. Basically, you want enough so that your averaging process is going to stabilise things, so that when you get a new data set, you don't get dramatically different results. But you don't want too many so that you're including neighbours that aren't really neighbours, because then you're going to start heading towards mean imputation. There's no real right answer, but it's worth playing around visualising the data. It depends a lot on the strength of the relationships between the variables in the data.